Okay, now we're going to go through paper 4, which is the theory extended option for chemistry, and that's for Cambridge IGCSE, and this is from Cambridge International Examination CIE, May-June 2018, so summer 2018, variant 2, so 0620/42. Let's get started.
So let's do this thing!
Question 1. Give the name of the process that is used, A, to obtain water from aqueous sodium chloride. Okay, if you have salty water, basically, you want to distill it if you want to get the water. Distillation. B, to produce lead from molten lead to bromide, and that is an electrolysis reaction. So electrolysis. C, to separate an insoluble solid from a liquid. Okay, you have sand in water, you want to separate it, you filter it out. So that's filtration. D, to separate the compounds of petroleum. Okay, different boiling points, you use fractional distillation. So fractional distillation. And E, to separate a mixture of colored dyes using your pen on a piece of paper, you use chromatography. All right, let's move on to question 2. Question 2. This question is about the elements in period 3 of the periodic table. We have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. For each of the following, identify a period 3 element which matches the description. Each element may be used once, more than once, or not at all. State which period 3 element A forms an oxide with a macromolecular structure. So basically a very big structure, and that is silicon. So it doesn't matter if you write silicon or you write Si. It doesn't matter. B, which one is extracted from the ore bauxite, and that is aluminium. C, which one is soft, metallic, and stored in oil? Well, that one's the one all the way at the left, sodium. Okay, sodium is stored in oil. So D, which one is a green gas at room temperature and pressure? That one is chlorine gas. E, which one provides an inert atmosphere in lamps? Inert means unreactive, so that would be the noble gas argon. F, which one forms 2 different oxides during the contact process? You only want one element that forms 2 oxides, and that would be sulfur. And G, which one is non-metallic and an important compound of fertilizers? And that one is phosphorus. So that's phosphorus. Question 3, complete the following table. Okay, so this is number of protons, electrons, neutrons, and nucleons. So remember, in an uncharged element, the number of protons and electrons are going to be exactly the same. In a charged element, well, the charge will make it so that they're not the same. The number of protons and neutrons added together is the number of nucleons. Okay, so what do we have here? We have 11 protons plus X number of neutrons makes up 23 nucleons. So that means this is 12. And this one, the small number is the proton number, so that is the number of protons, so that's 17. It says the large number is the neutron number, so that's how many nucleons there are. That is, says it's 37. And number of electrons, well, this has a charge of -1, which means there's one more electron than there are protons. So that means that has to be 18. Okay, and finally, we want to figure out which element this is. Well, to start with, we want to look at this proton number, because the nucleon number can change depending on what isotope it is. The number of electrons can change depending on if it's charged. So it is charged because the protons and electrons are not the same, but let's look at which element it is first. One. So 26. Okay, so if we look at the proton number, the small number, that element 26 is iron. So element 26 is iron. And as these two are not the same, we have 2 more protons than electrons, and it has to be Fe2+. Has to have a charge of 2 extra positives. Okay, and that's the end of this question. Okay, so question 4. Potassium reacts with bromine at room temperature to form potassium bromide. A. Write a chemical equation for this reaction and include state symbols. So potassium is K, and that is a solid at room temperature. Bromine is Br2, and that is a liquid at room temperature. Okay, and that produces potassium bromide, KBr. Just double check. So K is in group 1, so it's a charge of 1 positive, and Br is in group 7, so it's a charge of 1 negative, so it is KBr. So KBr is a solid at room temperature, and balance. We have Br2 here, so we have to have 2 Brs over here. Now that gives us 2 Ks over here, so we need 2 Ks over there, and it's balanced. Okay, that's it. B. Potassium bromide exists as an ionic lattice. Potassium bromide does not conduct electricity when solid, but does conduct electricity when it's molten. So 1. What is meant by the term ionic lattice? So an ionic lattice it contains both positive and negative ions. These ions are in a regular lattice structure. Okay, it has to be, you have to just, you can't just say lattice structure because it actually says it's a lattice. It's a regular structure. Okay, so it's made of positive and negative ions in a regular lattice structure. 3. Explain why potassium bromide does not conduct electricity when it's solid, but it does conduct electricity when it's molten. And the reason why is because ions, when they're in a solid, they can't move. But when they're molten, they are able to move. So ions in a solid can't move, but molten ions are able to move. Okay. C. Concentrated aqueous potassium bromide is an electrolyte. What is meant by the term electrolyte? Okay, so an electrolyte is a substance that is able to conduct electricity, and it has to be either molten or liquid or aqueous because it needs to also contain ions that can move. So an electrolyte is a substance that conducts electricity. It is molten or liquid or aqueous and contains ions. 2. Describe the electrolysis of concentrated aqueous potassium bromide. And in this answer, you have to include an ionic half equation for the reaction at the cathode, the name of the product at the anode, and the name of the potassium compound form. Okay, this is an electrolysis question, so remember to panic. So positive, anode, negative is cathode. The only time you should panic in a science exam. Okay, but I always write this whenever there's a question about electrolysis, even before I've read the question, because it often comes up about what's at the anode and cathode. This time it does. Okay, now the key here is it's aqueous. That means it's not pure potassium bromide. It also contains water. Okay, it's concentrated. It's mostly potassium bromide, but not completely potassium bromide. Okay, so at the cathode is negative, so it's going to attract a positive ion. Okay, so in here, we are going to have the ions we're going to have K plus, Br minus, and H plus, and OH minus. Those are the ions that we have. So the H plus is very reactive, more reactive, so it will be attracted to the cathode. So the equation, the ionic equation for this is 2H plus 2 electrons produces H2, and hydrogen is a gas that bubbles up. Okay, so the name of the product at the anode. So the anode is positive, and so the positive will attract a negative, and that will attract the bromine. So we have bromine is at the anode. Okay, and the name of the potassium compound form. So the potassium compound formed is basically what's left over. So that gives you a hint that it can't be potassium that's reacting at the cathode, because it has to have a potassium compound form. So the potassium compound form, we have potassium hydroxide. So potassium hydroxide is formed. Okay, that's the electrolysis of aqueous potassium bromide. 3. When molten potassium bromide is electrolyzed, the product at the cathode is different. Name the product at the cathode when molten potassium bromide is electrolyzed. Okay, when you have molten potassium bromide, you only have K plus and Br minus. That's it. You don't have any hydrogens or oxygens. So that means at the product at the cathode, the negative is cathode, it attracts the positive, so it has to be potassium. Potassium has to be at the cathode. Okay. D. Iodine reacts with chlorine to form iodine monochloride, ICl, as the only product. Write a chemical equation for this reaction. Okay, so if it produces ICl, it has to have I plus Cl. Now you don't get just plain I, it's always I2 and Cl2. Okay, and that produces ICl. Well, obviously, you have to have 2 ICl. And that's it. That's all it asks. That's all it asks for. So draw a dot and cross diagram to show the electron arrangement in a molecule of iodine monochloride. Show the outer shell electrons only. So iodine monochloride, ICl. Let's look at the periodic table. Okay, so we have I here and Cl here. So they're both missing 1 electron in their outer shell. That's it. They have 7 electrons in total in their outer shell. So we have ICl. We need to have the outer shells showing. Okay, so it doesn't matter which one is dots and which one is crosses, but in the middle, there'll be one of each. Okay, so let's say chlorine has dots. We have a pair there, and a pair there. Okay, so there are 7 dots in total in the outer shell of chlorine. They're paired, and these pairs are about as far away as they can be. One of the pairs takes 1 electron from iodine, and the same thing happens with iodine. But you use crosses, but it doesn't matter which one you use for dots and which one you use for crosses. That's it. Okay. E. Potassium bromide has a melting point of 734 degrees Celsius. Iodine monochloride has a melting point of 27 degrees Celsius. In terms of attractive forces, explain why there is a large difference between these melting points. Okay, now the reason why is potassium bromide is salt. It has an ionic structure, an ionic lattice, and that is a very strong structure. Okay, it takes a lot of energy to break ionic bonds. But iodine monochloride, if we look up here, it's a small molecule, and the molecules will be held together by intermolecular forces such as van der Waals forces. Okay, and they're a lot weaker. They're a lot easier to break. Okay, so let's write that down. So potassium bromide has strong ionic bonds. Iodine monochloride has weak intermolecular forces such as van der Waals forces. It takes more energy to break the ionic bonds in KBr. Okay. F. When chlorine gas is passed through aqueous potassium bromide, a redox reaction occurs. The ionic equation is shown. Okay, write an ionic half equation showing what happens to the chlorine molecules Cl2 in this reaction. Okay, so the chlorine molecule is going from chlorine gas to becoming an electron. Okay, it's gained, each chlorine atom has gained an electron. So what we say here, we start off, it says it starts off Cl2, and it has to have gained 2 electrons, 1 for each chlorine atom. And that makes 2Cl minus. You're just showing how did it get to become negative. Okay. And 2, explain why the bromide ion, Br minus, acts as a reducing agent in this reaction. So remember, well, this is the way that I remember which one is reduction, which one's oxidation. My teacher told me this when I was in high school. Leo the line says Gr. So loss of electrons is oxidation, gain of electrons is reduction. So chlorine has gained electrons. Chlorine is being reduced. That means bromide ions have lost the electrons, so they are being oxidized. Because bromide has lost the electrons, it's causing reduction in chlorine. It's basically giving its electrons to chlorine. It's a reducing agent. It's the agent of reduction. It's causing the reduction. So bromide ions are being oxidized, and because they are being oxidized, they are reducing agents. It can sometimes get a bit confusing, but that's just the way it works. Question 5. Hydrogen and iodine react together in a reversible reaction. Hydrogen iodide is formed. So we have H2 gas, and that's a colorless gas, and I2 gas, which is a purple gas, and in this redox reaction, 2HI creates a colorless gas. So on the left-hand side, it's purple because purple wins over colorless, and on the right-hand side, it's colorless. So the forward reaction is exothermic. A gas syringe containing an equilibrium mixture of hydrogen and iodine and hydrogen iodide gases was sealed and heated to 250 degrees Celsius. The equilibrium mixture was a pale purple color. Okay, so the gas syringe is just there so that they can change the pressure. That's it. That's why the end is blocked, so that they can change the pressure. A. What is meant by the term equilibrium? So equilibrium means that the rate of the forward reaction and the rate of the reverse reaction are the same. And that means that the concentrations of the reactants and products are the same. It doesn't mean that nothing's happened. It means that the rates of the reactions are going to be exactly the same, so it looks like nothing's happening, but the reactions are still taking place. So equilibrium means that the rate of the forward reaction equals the rate of the backward reaction, so that the concentration of reactants and products are kept constant. B. The plunger of the gas syringe was pressed in while the end of the gas syringe was blocked. That means this increased the pressure. The position of the equilibrium did not change. The color of the gaseous mixture, though, turned darker purple. Give a reason why the position of the equilibrium did not change, and that's because if you look at the equation, there's 1 mole of hydrogen gas plus 1 mole of iodine gas produces 2 moles of a colorless gas. So the number of moles on the left-hand side of the equation is the same as the number of moles on the right-hand side. So there are the same number of moles on both sides of the equation, and that only works in gases, but it does work in gases. 2. Suggest why the gaseous mixture turned a darker purple, even though the position of the equilibrium didn't change. And that's because, yes, there was the same number of iodine molecules, which are the purple, but they were in a smaller space. So the same number of I2 molecules are now in a smaller volume. And that's why it's a darker purple, even though there's the same number of molecules. C. The temperature of the gas syringe was now increased to 300 degrees Celsius. 1. What happened to the position of the equilibrium when the temperature of the gas syringe was increased from 250 degrees Celsius to 300 degrees Celsius? And remember that it said the forward reaction is exothermic. So when you increase the temperature, basically the reaction tries to cancel out what you've just done to it. So that means the equilibrium moves towards the reverse reaction. So the equilibrium moved towards the reactants. 2. What happened to the rate of the forward reaction and the rate of the backward reaction when the temperature of the gas syringe was increased from 250 degrees Celsius to 300 degrees Celsius? Well, the rates of both the reactions increased, because when you increase the temperature, you increase the rate of the reaction, except with enzymes, and then enzymes, if you've gone past their optimum temperature, they will denature and the reaction will go slower. So as the temperature increased, both the rates of reactions increased. Question 6a. All sodium salts are soluble in water. All nitrates are soluble in water. Barium carbonate is insoluble in water. Describe how you would make a pure, dry sample of barium carbonate by precipitation. And remember, precipitation reactions require 2 aqueous solutions. So what's it asking for? It's asking for a sodium salt, it's asking for a nitrate, and it wants barium carbonate. So that means we're starting with we need some Na+, if we're using all the information in the question, because it'd be kind of silly for them to put in information that's not needed. They don't tend to do that at GCSE. You need a nitrate, so it's NO3-. You need barium, that's Ba2+, and a carbonate, CO3 2-. Okay, so those are the ions you're working with. So describe how you would make a pure dry sample of barium carbonate by precipitation. You have to include the names of the starting materials, the full practical details, and a chemical equation. Okay, so let's start out with the chemical equation. We have to end with barium carbonate. It's basically barium has to swap its partner with sodium. So we start off, we have to have sodium carbonate to start with, and sodium carbonate, Na, it's Na+, I'm mixing with a carbonate, 2-, so we swap the 2- and the plus, so it's Na2CO3. Okay, and then we have to add it to barium nitrate. So Ba, do have a 2+ here and a minus there, we have to swap them again. BaNO3 2. All right, and then we want to end up with barium carbonate, BaCO3, and what do we have left over? We have NaNO3, and they're both 1+, so 1-, so that's 1 to 1. So we have 2 NAs here. That means we need 2 NAs here. That means we now have 2 NO3s, which we have 2 NO3s here. We have 1 barium, 1 carbonate, and 1 carbonate. So that balances. That is the reaction it starts with. Because you want to end up with barium carbonate, you need a sodium salt, you need a nitrate, and that's it. So the barium carbonate, that is the solid precipitate. That's what you're looking for, because barium carbonate is insoluble in water. Okay, so we've done the chemical equation. Now let's do the names of the starting materials. Okay, so it says the names of the starting materials. It doesn't say the formula of the starting materials. You have less chance of going wrong if you just write out the name than the formula. Yes, you wrote the equation here, but if you got that wrong, you don't want to lose 2 marks for it. So basically you start by mixing aqueous sodium carbonate and barium nitrate. So you start by mixing aqueous sodium carbonate and barium nitrate. When it says here up here the chemical equation, that does not say to include the state symbols, so you don't need to include those. But this is part of the procedure, so you do need to say that they're aqueous, because to do a precipitation reaction you need to mix 2 liquids. Okay, and when you mix them, you will have a precipitation reaction. You will have a solid formed. What do you do with the solid? You have to filter it out. So you filter out the precipitate, which is barium carbonate. And then you have to wash that residue and dry it. So wash and dry the residue. Okay, and that's all you have to do. So wash with pure water, and then you dry it, and then you have pure barium carbonate. Okay, good. B. Nitrates decompose when heated. Write a chemical equation for the decomposition of sodium nitrate when it is heated. Okay, so we have sodium nitrate, NaNO3. Okay, its decomposition is just talk about heating something, one thing, and having it break down. So there's only one thing in the reactant side. Okay, when you heat it, you have to get something different. Okay, the thing that will break off is some oxygen. So you get NaNO2, because you don't, NaNO isn't a molecule that you'd get, or NaN, those aren't molecules you'd get. NaNO2 is a real molecule, basically, and you add it to oxygen. Okay, now clearly that is not balanced. Okay, there's the same number of sodiums, but nitrogens, yes, there's the same number, but oxygens, no. So we have 3 on this side, and we have 4 on this side. So what can we do? Well, there's a couple things we could do. Let's start by putting a 2 in front of here and see how that works. If we put a 2 in front, and this is how you can balance equations like this quite often, you just have to do trial and error, but simple ones. Okay, so put a 2 in front of here. You have 2 sodiums, so you need 2 sodiums over here. When you do that, you have 2 nitrogens, and you have 2 nitrogens. That's the same. And you have, how many oxygens do you have? You have 6, so 2 times 3 oxygens. Over here, you have 2 times 2, that's 4, plus 2, that's 6. So that balances out. That's the equation. Good. 2. The unbalanced chemical equation for the decomposition of hydrated copper 2 nitrate crystals is shown. Balance the chemical equation for this reaction. Okay, this one's a bit more tricky, but it's still the same thing. You just have to trial and error it. So I'll do it in pencil first. Okay, so we have 2 coppers over here, which they're saying don't change this. This is the same. Oh, this is the trick. So when you have the dot, that's the hydrated. That means there's not 6 hydrogens. There are 6 times 2, that's 12 hydrogens. Okay, so you have 2 coppers. We need 2 coppers. Okay, we have now how many nitrogens? We have 2 times 2, that's 4 nitrogens. Okay, let's try putting a 4 in front of there. Let's balance the oxygens last because they're in more things. Let's try the hydrogens. We have 3 times 2, that's 6, times 2, that's 12. Okay, that's for the hydrogen. So 12 divided by 2, that's 6. Okay, so we've done that. Now let's check to see if that makes sense with the oxygens. Okay, so we have 6 oxygens here, plus 2, that's 8, plus 8, so that's 16, plus 2, that's 18. Okay, there's 18 oxygens on the product side. On the reactant side, we have 3 times 2, that's 6, times 2, that's 12, plus 3 times 2, that's 6. So that is also 18. So it's 18 oxygens on both sides. As I said, the trick is that this 3 waters, is included in this 2. So it's 2 times 3 waters. So it's 6 waters. It's 1 water for every salt. Okay. 3. When the hydrated copper 2 nitrate crystals are heated, steam is produced. When the steam condenses on a cool surface, it turns into a colorless liquid. Anhydrous cobalt 2 chloride is used to show that the colorless liquid contains water. How does the color of the anhydrous cobalt 2 chloride change? This is a very pretty reaction. I love doing this one. It goes from blue, a nice pretty blue, to a nice pretty pink. Okay, and 4, how would the student test to determine if the water produced in B3 is pure? Basically, you can check the melting point or the boiling point or the freezing point. So check if the boiling point is 100 degrees Celsius. So you want to check that the boiling point is a sharp 100 degrees Celsius. Question 7. Many organic compounds such as alcohols, carboxylic acids, and esters contain the elements carbon, hydrogen, and oxygen only. A. Compound R has the following composition by mass. It's 60% carbon, 13.33% hydrogen, and 26.67% oxygen. Now you need to calculate the empirical formula of R. So first of all, we have a ratio here of 60.00 to 13.33 to 26.67. However, you're not working with the same things. You need to work you need to work with the number of actual moles. That's just by mass. You need to do it by moles. So moles equals mass over relative molecular mass. So this is the mass. We need to divide each one of these by the relative molecular mass. So the relative molecular mass of carbon is 12, hydrogen is 1, and oxygen is 16. So that gives you a new ratio of 60 divided by 12, that is 5. 13.33 divided by 1 is 13.33. And 26.67 divided by 16, that is 1.67. Okay, so if you take those, now you can take those and divide by the smallest number. You need to divide by mole, the smallest number of moles. So if you divide each one of those by 1.67, which is the smallest number, you get a new ratio. 5 divided by 1.67, rounding it up just a tiny bit, is 3. 13.33 divided by 1.67, rounding it up just a tiny bit, is 8. And then 1.67 divided by 1.67 is 1. So that means the empirical formula is C3H8O. Good. And B, compound S has the empirical formula C2H4O and a relative molecular mass of 88. Calculate the molecular formula of compound S. So if the MR of C2H4O equals, so the relative molecular mass of C2H4O is 44 grams per mole. Okay, now we need to figure out, trial and error again, how we can turn 44 grams per mole into 88. So let's say if we multiply it by 2, that creates C4H8O2. So let's check that. The MR would now equal, that is 12 times 4 plus 8 times 1, or 1 times 8, plus 16 times 2. And that equals 88 grams per mole. So that means the molecular formula is C4H8O2. If this didn't add up to the right number that you're told it is, then you'd try multiplying it by 3. They won't go up very far, don't worry. C, compounds T and V both have the molecular formula C3H6O2. Compound T produces bubbles of carbon dioxide gas when it is added to aqueous sodium carbonate. Okay, and compound V is an ester. Okay, so what is the name given to compounds with the same molecular formula but different structures? Those are called structural isomers. Okay, they're structural isomers. Okay. And 2, draw the structures of compounds T and V and show all of the atoms and all of the bonds. Okay, so compound T produces bubbles of carbon dioxide gas when it is added to aqueous sodium carbonate. That sounds a bit like a carboxylic acid. So carboxylic acid, okay, remember that has the C double bond O, OH. Okay, you don't draw this part in there. That's just to show you. Okay, so we have C3H6O2, both these, so you have to put 3 carbons down. And we have to have one of the end carbons, it doesn't matter which side, has to have, and don't forget to draw the bond between the O and the H. It's still a bond, it says draw all of the bonds. Okay, and then all the rest of the carbons have to add up, so their bonds have 4, so there's 4 bonds for every carbon. Okay, so with hydrogens. Okay, so that is for compound T, a carboxylic acid. Okay, compound V is an ester. So an ester has a COC, and on one of the carbons, there's a double bond O. Okay, so we have 2 things we can do. We can go COCC and put a double bond O here. And we remember need 4 bonds, 1, 2, 3, 4, so that would be an H. And these have to all add up to 4. H, 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 H. Or we can do the same thing. C, O, C, C. We can put the double bond on here, and that already has 4 bonds now. And fill the rest of the H's up. Okay, so one or the other, it doesn't matter. Just draw one of them. You don't know which one. It hasn't been specific. Okay, there you go. 3. All compounds with the molecular formula C3H6O2 can undergo complete combustion in an excess of oxygen. So complete the chemical equation for this reaction. So all combustion in oxygen reactions, it says in an excess of oxygen, so it means that you're not going to get carbon monoxide. You have to obviously react in oxygen, and you get CO2 and water. Now we just need to balance it again. So we have 3 carbons here. We should have 3 carbons here. We have 6 hydrogens here, so we should have 2 times 3 to make 6 hydrogens here. We have 2 plus 2 oxygens here, and here we have 3 plus 6. That's 9 oxygens. Okay, now can you do that? So we have 9, so you need 7 oxygens over here because you already have 2 here. 7 divided by 2, that's 3.5. So you can actually say 3.5 oxygens. If that bothers you, you can always put a 2 in front of here and multiply, make that 7, the 6, and the 6. However, there are the lines here. There's no dotted line to add here. You can do that. It works either way. Okay, but you are allowed to do a fraction for a molar quantity, especially in front of oxygen. Okay, D. Compound W has a molecular formula C2H6O. Compound W reacts when heated with ethanoic acid and a catalyst to produce a sweet-smelling liquid. Well, it's producing an ester. Okay, so an ester, remember, that is an alcohol plus an acid with a catalyst produces an ester. Okay, so give the name of the homologous series to which compound W belongs. Compound W is not the product. Compound W has a molecular formula of C2H6O and it reacts with ethanoic acid. That means it is an alcohol. It says that there's 2 carbons. That doesn't mean you should write ethanol because it says the name of the homologous series. It doesn't want the name of the molecule. Okay, so the answer here is an alcohol. Draw the structure of compound W. Show all of the atoms and all the bonds. Well, you know that there's 2 carbons. You know one of them is an alcohol. One of them attaches to an alcohol. Remember, it says all of the bonds, so you have to draw the OH bond, and then all the carbons have to add up to 4 bonds. There we go. That's it. E. Alkanes and alkenes are hydrocarbons. What is meant by the term hydrocarbon? This has come up on many exams. It is a substance that only contains carbon and hydrogen. So a hydrocarbon is a substance that contains only carbon and hydrogen. And state the general formula of alkanes. That is CnH2n plus 2. And alkenes, that's CnH2n. Because remember, C, we have 1 hydrogen for every 2 hydrogens for every carbon plus 1 at the end, however long the chain is. But for an alkene, we take away 1 of those hydrogens, so we only have 2 hydrogens for every carbon. F. Ethanol can be produced from long chain alkanes as shown. So we start it with a long chain alkane. We have to obviously break it because ethene only has two carbons. And then we have to add an alcohol to make it into ethanol. So describe the 2-stage manufacture of ethanol from the long chain alkane octane, C8H8, and you have to include the names of the types of chemical reactions that occur and the reaction equations and the reaction conditions. Okay, so step 1, you have to break the long chain into pieces. That is called cracking. So it's a cracking of octane. Okay, step 2, the turning it from ethene with a double bond, breaking the double bond and adding an OH to one and an H to the other side of the double bond. That's called hydration. So step 1 is cracking of octane and step 2 is hydration of ethene. Okay, the reaction equations. When you crack octane, you go from C8H18, which it already tells you up here, and you just break it basically with a catalyst. That's C2H6O. H4, which you've already worked out is the formula for alkenes. And yeah, you have those 2 carbons there, so you have to have the rest of the carbons. There's 6 carbons, C6H14 has to add up to what you started with. You're not losing anything. Okay, and the reaction conditions here, it's about 450 degrees Celsius to 800 degrees Celsius. Okay, and you have to use a catalyst. And so there's lots of catalysts you could use. Aluminium oxide is one catalyst. Okay, other catalysts you could use. You could say zeolites, aluminosilicates, silica, SiO2, alumina, you could say china or a broken pot, chromium oxide, or CrO3. Any of those would have been acceptable. And it occurs at up to 70 atmospheres of pressure. Okay, so hydration of ethene, well, that you start off with C2H4, and hydration means you add water plus H2O, and you get C2H5OH. You get ethanol. Okay, and the reaction conditions for this, we have phosphoric acid, which is H3PO4, at 300 degrees Celsius and 60 atmospheres. All right, that is the end of this exam. I hope you have found this useful. If you have, please press the like button and the subscribe button. We'd really appreciate it. And if you have any questions, comments, or anything else you'd like to say to us, please write them in the discussion section below. We'd love to hear from you. And have a great day.